So let us continue and hopefully finish chapter 27. So remember, so far we covered the main equations that govern circuits are Ohm's law, V is equal Ri, and we did Kirchhoff's loop equation and junction equation. Okay, so in any circuit, after you label all your variables and determine the directions of your circuit, you assume a certain direction for the currents, okay, and you label everything. You can write the junction equation for your circuit. So this is the junction equation here. Sum of the currents is equal to 0. And we usually take currents moving into the junction positive, current moving out of the junction as negative. So we sum all of the currents at any junction, they have to be 0. This has to do with conservation of charge. The second equation is the loop equation. If you go around the loop, whether it's in the clockwise direction or counterclockwise direction, if you start at a point and you go back to the same point, the sum of the potentials should be equal to 0. And this has to do with the conservation of energy. It's like if you go on uphill and downhill and so on, and you come back to the same level, the change in potential energy is going to be 0 because rho mgh is going to be 0. So if you go up here, downhill, and so on, and you go back to the same level, and you determine the change in gravitation potential energy, it's 0. Same thing in a circuit. If you go from one point and you go back to the same point, you find that the delta V, or the sum of all of the potential differences, is equal to 0. It's very important to remember the convention for pluses and minuses. So if you're going in a loop direction and you go through a resistor, if you're going in the same direction as a current, the potential decreases, so it's minus Ri. If you go opposite, if the direction of your loop is opposite the direction of the current, then it's plus Ri. If you are going through a loop and you go through a battery, if you enter the battery from the negative terminal, the potential increases, so it's plus epsilon. If you go through the positive terminal of the battery, the potential will decrease, so it's minus epsilon. So these are the conventions we have used for writing loop equations. So, okay, and we did a couple of examples, and I think the last example we stopped was this one, and we wrote the junction equation, and we wrote the loop equations for this circuit. And if you remember, so at the junction C, actually, so at the junction C, you have plus I1 okay, so here at this junction you have plus I1 plus I2 minus I3 is equal to 0. So this is a first equation. Last time we also wrote the loop equation, and here we chose to be going in the clock direction, clockwise. So if you were going through, let's see, did we go through loop 1? Yeah, so loop 1, I think this is what loop 1 here, loop 2. So we go through the potential, the battery, through the negative terminal, so it's plus 10 volts. Then we go in the same direction as the current, minus 6 ohms times I1. Then we go through this resistance, and we go in the same direction as current I3, so it's minus 2 ohms times I3 is equal to 0 because we went back to the same point B. Okay? Then we wrote the loop equation for the second loop, and we started also at point B. Okay, so when we go through the 4 ohm resistor, we are going in the same direction as I2, so it's minus 4 I2. Then we go through the battery, through the EMF, so it is, and we're going through the positive terminal, so it's minus 14 volts. Then we come back here, so we're going through the 6 ohm resistor, but against the direction of the current, I1, so it's plus 6 I1. Then we go through the EMF 2, and we go through the positive terminal, so it's minus 10 volts, and we go back to the same point, so this is equal to 0. So now you have 3 equations with 3 unknowns, and you can solve them by substitution or whatever. And so now, after you do that, you find a current I1 is 2 amps, the current I2 is minus 3 amps, and the current I3 is minus 1 amp. So clearly, the directions of the current for I2 and I3 are wrong. Okay, so after we have finished the solution, we can now correct this. We can say the direction I3 is really like this. Okay, and same thing for I2. We say the direction of I2 is really in the opposite direction. So after you have finished the solution, you find negative numbers for your currents, you can correct that. Okay, clear? Any question about Kirchhoff's loop and junction equation? This is, if you know this, you can solve any for any simple circuit that has linear components. Okay, obviously in electronics you can have non-linear components like diodes and transistors and so on. Okay, so I want to draw your attention to the following. Okay, if you have 2 junctions, like in this circuit here, then writing the equation for first junction and the second junction and the second junction will not give you more information. Huh? So it will be, so if we write it for junction A, we can see I3 is equal I1 plus I2, or let me write it, sum of the currents equal to 0. So I will write it like this. So current moving into A is positive, so we have, and moving out. So we have minus I1 minus I2 plus I3 is equal to 0. This is how I write my equation, okay? Now if you write it for this junction, okay, so current moving in, you have I1, and you have I2 is moving in also, plus I2, and minus I3 is equal to 0. So you can see that equation 2 is just minus 1 times equation 1. So you don't gain any information. So these 2 equations are the same here. So it doesn't help you. Okay? Same thing when you write loop equations. Let me give you an example. So here we have already written equation for loop 1 and equation for loop from the previous example. Okay? And this is a circuit where you have 3 unknowns, I1, I2, and I3. So you need 3 equations. Let's assume you say, okay, let me write the loop equation for this larger loop, loop 3. Okay? So if you go through loop 3 and you write the equations, you will, let me write it here, okay? So let's start at this point here, okay? So we're going through a resistor R5 in the same direction of the current, so it's minus R5 I1, okay? Then you go through this resistor R4, and you're going in the same direction as the current I3, so minus R4 I3. Then you go through this EMF through the negative terminal, so it's plus epsilon 3. Then you go through resistor R3 in the same direction as the current R3, so it's minus R3 I3. Okay, then you go through resistance R1 and you're going in the same direction as current I1, so it's minus R1 I1. Now you're going through the EMF E1 epsilon 1 and you're going through the positive terminal, so it's minus epsilon 1. We go back to the same point. This is equal to 0. So this is a third equation, a third loop equation. The problem is this equation is just the sum of the previous 2. So this is the equation we just have written. Notice if you add equation 1 and equation 2, you will get equation 3. So these are now not independent equations. We don't have 3 independent equations. We have still only 2 independent equations. The third one is just the sum of the first equation plus the second equation. So you can only use 2 of these three equations. And this one is just the sum of this one and this one. So it does not give you more information. Okay? It does not give you more information. And so in a circuit like this, you have to use loop 1, loop 2, and junction. One of the junctions. Okay? So this is just an aside so that you do not use dependent equations. You have to have three. If you have three unknowns, you have to have three independent equations to solve for three unknowns. All right? All right. Now this is an important aside. So here we have an EMF, a real EMF with an internal resistance R and external load resistance capital R. So we have a current I. Okay. Let's assume I want to determine the potential difference, VB minus VA. Okay. So one way to do that is I indicate a direction through which I go from point B to point A. Okay. And so I'm going to start at point B. Now this is another one. Let me start with this one first. Okay. So here I'm starting at point B. Okay. Then I'm going through the resistance in the same direction as the current. So it's minus IR, and I reach point A. So that's equal to VA. So VB minus RI is equal to VA. So now I can write VB minus VA. So actually, so VB, this really should not, so first of all, we get this one, this equation here, and we know the current is, we have the EMF and we have the resistance, the equivalent resistance capital R plus small r. So really, we can replace the current by this equation, which is capital R divided by, epsilon divided by R plus small r plus capital R. We multiply it by R. So this is now the potential difference across the battery. Remember, this is a battery. This is really a battery. And these are the terminals of the battery. This is an internal resistance of the battery. Now I can do the same thing. Instead of going through this direction, I can go in the other direction, the blue one. Okay, so let's write the equation for the blue one. Okay, so here I start at point B, then I go through small resistance R in the opposite direction as the current, so it's plus IR. Remember, this is the current I. We're going in the opposite direction. Then we're going through the EMF through the positive terminal, so it's minus epsilon. We reach point A, so this is equal to VA. So now we can write VA or VB minus VA is equal epsilon minus RI. Okay, and since we know the current I is just equal small r plus capital R, if we replace the current, we obtain the same equation as before. So this is the equation that we get, which is the same as this one. So it doesn't matter which direction I go. If I want to determine the potential difference between 2 points in a circuit, I choose any direction from one point to another, and I write the equation. So I start at VA, go through the potential differences until I reach that point, and set this is equal to this voltage at this point. Then I can rearrange the terms and get the potential difference between those 2 points. Any direction will do. So the potential difference between any 2 points in a circuit does not depend on the path taken. Okay, so it should give you the same result. Now, this is the method to find the potential difference, VA minus VB, between any 2 points A and B in a circuit. Start at point A, which has a potential VA, and traverse the circuit to the other point B, following any path, and add algebraically the changes in potential you encounter to find VB, and rearrange the terms to find VA minus VB. This is a little bit more difficult. When you solve the circuit and you find I1, I2, I3, you might have a question that will tell you what's the potential difference between this point in the circuit and this point in the circuit. So this is how we do it. So you start at that point, you go take any direction to reach the second point, and keep adding the potential until you reach that point, and you rearrange the terms, you can find the potential difference between those 2 points. Let's do an example. All right, so here is a circuit. All right, it's a simple circuit. We have 2 batteries, real batteries, with internal resistance R1 and R2, and EMFs E1 and epsilon 1 and epsilon 2, and we have an external load resistance. What is the current in the circuit? So in order to solve for the current in the circuit, I can choose a loop. So I chose the loop in this direction, which is counterclockwise. Let me start at point A. So let's start at point A and write the equation. So if I start at point A, I'm going to go through resistance R1 opposite to the direction of the current. So plus R1 times I. Then I go through the EMF from the positive terminal, so it's minus sigma 1. Then I go through the load resistance capital R and the opposite direction of the current, so plus Ri. Okay, then I'm going to go through the negative terminal of the second EMF, so it's a plus epsilon 2. Then I'm going through resistance R2, smaller resistance R2 of the second EMF, and we're going in the opposite direction of the current, so plus R2I. Now I want back to the same point I started with. So this is equal to 0. So now I can write the current I, okay, it's just equal to sigma epsilon 1 minus epsilon 2. These are the EMFs divided by R1 plus R2 plus capital I. Okay, so when you become very good at writing the loop equation will help you determine the current. Okay, then the next question, what is the potential difference across the terminals of battery 1? So these are the terminals of battery 1. Let me call this point A. Oh, it's already named A. Okay, and this point is B. So they are already named. So I want VA minus VB. The method is, let me start at A and let me pick a direction. So let me pick this direction here, and I want to reach point B. Okay, so I'm going in this direction. Okay, so I write VA. Now I'm going through resistance R1, small r1, opposite direction to the current, so plus R1I. Then I'm going through the EMF epsilon 1, I'm going through the positive terminal, so it's minus epsilon 1. I reach point B, so I write this is equal to VB. Now I can rearrange the terms. VA minus VB is going to be equal to epsilon 1 minus R1I. Since I have the equation for I can replace it, or the value, so I can calculate this actually. So this is 4.4 minus 2.1, 0.9, 4.4, so 2.4, 2.3, this is 2.3 volts divided by the sum of the resistances, 2.3 and 1.8, that's so 3, 4.1, 4.1 plus 5.5, so this 9.6 divided by 9.6 ohms. So you get the current, you can replace it here, and you get the potential difference between the two terminals. I could have gone also the other direction. If I have gone the other direction, which is a little bit awkward because I'm so I can go also this other direction, but I will be going through more components. So it will take me longer, but I should find the same final result. Okay, so let's look at the values. Is it clear how we can go from one point to another to determine the potential difference? You start at one point, you pick a direction how you're going to go in the circuit, and you start adding the potential, paying attention to the convention that we took, until you reach the second point. And that will give you, then you rearrange the terms to get VA minus VB. Okay, so this is the first question. You get 240 milliamps And the second question, so this is we went same, they took the same path, VA minus R1I minus epsilon 1 is equal to VB, and we get VA minus VB is 3.84 volts. Makes sense, because the EMF has 4.4 volts, but that's not what we're going to get, because some of the voltage is lost through the internal resistance, so we get something less than that, because the internal resistance is not small. Actually, R1 is 2.3 ohms. That's quite high compared to the other resistances in the circuit. Okay, so this is a good example because it has, first of all, we are doing a loop equation, Kirchhoff's law. We are using Ohm's law. Whenever we go through a resistance, the voltage differences are I, okay? And we are using real batteries because they have internal resistance, and we are also trying to find potential difference between 2 points in the circuit. So this is an example. It's a simple example, but it illustrates many important concepts. Okay, so this is a repeat of the previous method. Okay, now this is an aside. I decided to cover it because when you are connecting circuits, usually you ground your circuit. This is a safety measure. We always connect any instrument to the outlet, and the outlet, one of the wires is connected to ground. Okay, so this is the symbol we use for ground. Okay, and whenever we ground a circuit, that means the voltage at that point is zero. The ground is connected to the earth surface. It's a big reservoir of charges. So whenever we connect a circuit to ground, the voltage at that point is zero. Okay, so this is what we call ground. Grounding a circuit means connecting the circuit to a conducting path to the earth surface. Such connection means only that the potential is defined to be zero at the grounding point in the circuit. It does not affect the changes of potential. Delta V's are going to be the same in your circuit. The delta V's, the potential differences are still going to be the same. The only thing is now that point has zero voltage. Okay, so for example, this ground here tells me that VA has to be equal to zero because it's connected to ground. Okay, so in the previous example, we determined the current I, which is the EMF epsilon, or here divided by the sum of the two resistances. Actually, here we have only one EMF and capital resistance R and small resistance R. So this is 2 amps. Okay, we also we have VB minus VA is the equal to the EMF minus RI. Okay, the EMF is 12 volts minus R, which is 2 ohms, times I, which is 2 amps, will give you 8 volts. So the difference, VB minus VA, is 8 volts. Since VA is equal to 0, that means VB is going to be equal to 8 volts. So that means if you connect this circuit and it is grounded, and you bring a voltmeter, if you bring a voltmeter, so this is a voltmeter, okay, usually you connect the ground to ground. Then you take the other point of the voltmeter and you start moving in the circuit and measuring voltages. So if you connect the other point here, you will measure 8 volts. If you connect it here, you will measure 0 volts. So if you connect the 2 points of the voltmeter to the same point, this is 0 volts. Okay, and you can move in the circuit and measure the voltages, all the voltage in the circuit, using a voltmeter. Okay, so let's illustrate how we can change the ground. Let's assume we take another point as a ground. So instead of connecting it this way, we're going to connect ground to another point. So here, instead of connecting ground to point A, we're connecting the ground to point B. Okay, the potential differences are not going to be affected, but the values are going to be different. Okay, so notice now VB is equal to 0, not VA. So this now VB is equal to 0 because it's connected to ground. But VB minus VA is still 8 volts. So since VB is equal to 0, that means VA is going to be equal to minus 8 volts. So notice here VA was 0 and VB was 8 because of the grounding. And now, because we move the ground here, VB now is equal to 0 because it's grounded. That's where we have the connection to ground. And VA now is minus 8. This is particularly important for those who are in electronics or computer engineering, electrical engineering, and so on. Usually, we have to connect your circuit to ground. This is a safety measure we take to protect people who are using this instrument. So if there is a short, it will go to the ground. It will not, if you touch the metal outside, if this is not grounded and there is a short circuit, if there is a short circuit and this metal is connected to ground, all of the extra charge will go to ground. Okay? But if it's not, and I touch it and there is a short, I will get electrocuted. So usually we connect our circuits to ground as a safety measure. Okay, so this is grounding. A point in a closed circuit will change the voltage value, but it will not change the voltage differences. Delta V's are going to be still the same. It's just the V values of V's will be different. Okay? In your labs, you are going to use voltmeters and ammeters. A voltmeter is usually connected in parallel. So if I want to determine the voltage between point C and point D, I just bring the voltmeter and connect one side to point A, one side to point B, and measure the voltage. Very easy. Okay? Usually the voltmeter has a very high input impedance so that it does not affect the circuit. This has the impedance or the resistance is very high, and let's say it very high, so that it does not, there is no current flowing here, or zero current flowing here, almost zero. So usually a voltmeter, when we connect it, it does not affect our circuit. We don't want it to affect the circuit because we want to measure the voltages at 2 points in the circuit. Okay? However, if I want to measure the current, it's a little bit more tricky. I have to break a connection. Let's assume I want to measure the current in this branch. So what I have to connect, I have to bring the ammeter, break the connection, and connect my ammeter like this. So now it's in series in this branch, and then the current will flow through it. Usually, the ammeter has a very low impedance, very low resistance, so it does not affect my circuit. So R here is approximately 0. For the voltmeter R, the impedance is approximately infinity, very large. For the ammeter, it has to be very small, so it does not affect the current in the circuit. So these are two instruments that you use in the lab. I just wanted to make sure you know about them. Are you doing circuit experiments in the lab or not yet? You started, huh? Okay. Okay, so this is an aside about voltmeters and ammeters. Okay. Now we come to the last section of the, which is charging a capacitor, RC circuits. Usually, we have a battery, and let's assume this switch here is not connected to any place, and we have a capacitor C and the resistance R. Okay, if I want to charge this capacitor, I can switch the switch to this position, and it will be charged. Okay, remember, when we studied capacitances, we said when you connect it, the potential across the capacitor will match the potential here. So eventually the potential across the capacitor will be equal to the EMF. So the potential will increase. Okay, the charge will also increase, and we will obtain a charge Q. Okay, now in order to determine the current and voltage and so on, we can write the loop equation. So we can analyze the circuit with the loop. So let's write the loop equation here. So now I switched the switch to this position A, and I chose the loop equation in this direction, which is clock direction. Okay, so let's start with the point here. So we're going through the so now we're going through the EMF, in the negative terminal of the EMF, so plus epsilon. Then we go through the resistor, and this is the current direction we assumed. Okay, so the current, we are going in the same direction as the current, so it's minus capital R times I. Now we reach this potential, and this is usually the positive and the negative terminal of the capacitor. So now we are going to decrease the potential from one side to the other, and we know Q is equal CV, C delta V. Okay, so I can write delta V of the capacitor is just equal Q over C, and that's what I have here. In fact, I'm using minus sign because I'm going to do the positive terminal of the capacitor, or the terminal or the side of the capacitor that will have positive charge. Okay, so now we have an equation. This is a differential equation because Q, remember Q is di dt. So let's replace it. So we replace I, the current, by dq dt, and now we have a differential equation that we want to solve. Have you studied differential equations? You did. So this is not a difficult differential equation. We can, the initial conditions we have, initially that at t equal to 0, the capacitor has 0 charge, was not charged initially, and the current through, I will mention this later, when you just switch the turn on the switch, or the capacitor acts like a connector. So the potential or the current is going to be the EMF divided by the resistance of the circuit R, okay, at time equal to 0. So this is an initial condition or boundary condition for your differential equation. At time t equals to infinity, we know that the charge of the capacitor is going to be equal to C times the voltage, because we have Q is equal C times the voltage, and the voltage will be the same as the voltage of the EMF. And at infinity, or in steady state, there is no current flowing in the capacitor. Okay, so there is no current flowing through capacitor. The current is 0. Okay. So actually, the current, all of the currents that are flowing in the circuit, they are flowing in this part of the circuit, and they are flowing in this part of the circuit. They are not flowing through the capacitor. Remember, capacitor has a dielectric material. It's an insulating material. It's a redistribution of charges, but really there is no flow of charges in the capacitor. Remember that. Okay, so let's solve this differential equation. Okay, so let's rearrange the terms. Okay, so if we rearrange, we can write dq dt is equal epsilon divided by r minus q divided by rc. So we can further rearrange the terms. We can bring the dt in this side, and so this becomes dq over q minus c epsilon is equal minus 1 over dt. We can integrate both sides and solve. And when you integrate both sides, this is 1 over q minus the constant dq, and when you solve, you find that this is the log, the integral of 1 over x is log of x. So eventually, you find this is the equation, the solution for your differential equation. If you take the exponential of both sides, you end up with this equation. So the charge Q is equal to the charge at infinity, t equal to infinity, times 1 minus exponential minus t over rc. Okay, this means, let's verify first of all if the initial conditions are satisfied or not. We said at t equal to 0, the charge has to be 0. At t equal to 0, exponential minus 0 is 1. 1 minus 1 is 0. So at t equal to 0, the charge is equal to 0. Okay? Now, we also said t at infinity, the current is going to be 0. Okay, so let's determine the current. The current, remember, is dq dt. Okay, so you will find that this is going to be equal to, all right, so if we take the derivative, so CE 1 over RC, so this is E over R exponential minus t over RC. Okay, when t goes to infinity, exponential minus infinity is 0. So at t equal to infinity, the current is also 0. Okay, so the differential equation, if we plot it, if we plot the charge versus time, this is what you get. You get an exponential increase. When t goes to infinity, the maximum value is c times the EMF, which is epsilon, CE. So this is the, when t goes to infinity, you get a value of C epsilon. Okay, and at t equal to 0, the charge is equal to 0. At t equal to infinity, the charge is equal to maximum charge, which is CE. Okay, and one thing is, when we have an exponential increase or exponential decay, at time t equal to RC, at the time t, tau, equal to RC, we get, if we replace t by RC, you will have exponential minus 1, which is 1 over E. 1 minus 1 over E will give you 0.6 something, 0.63. So at time t equal to RC, the exponential of minus t over RC becomes exponential minus 1, and this is 0.63 times this charge, which is the maximum charge. Okay, this is what we call the time constant. RC is the time constant of this circuit. It's R times C. And the reason we say it's time constant, because if you look at the units, you will find that it's in units of time or seconds. This is, so again, this is the charge. Now, if you look at the current, we said the current is a derivative of the charge with respect of time, dq dt. And dq dt is, if you take the derivative of this equation, this is what you get. You get, this is epsilon over R, which is the current at t equal to 0. Okay, and so this is the current here. This is epsilon over R. Okay, exponential minus t divided by RC. So at t equal to infinity, or reaching infinity, the current will be 0. Okay, now when you analyze a circuit and you are switching switches, these are very important remarks. At t equal to 0, things are happening very fast. You can assume the capacitor acts like a connecting wire. You can assume as if there is a connecting wire. So at t equal to 0, you can assume there is like a connecting wire. It's not there, but you can assume, and you can actually get the current. You have just the EMF and the resistance. You can get the current is the EMF divided by the resistance R. This is at t equal to 0. Okay, just when you switch and you start charging the capacitor. Okay, at t equal to infinity, you can assume the capacitor acts like an open, meaning as if there is a broken wire. So I can assume at t equal to infinity as if there is no connection here. So this is what we're symbolizing here. That means there is no current flowing in the capacitor. And we know this is at t equal to infinity, the current has to be equal to 0. So when you solve a problem, and the problem of the statement of the problem, it says immediately after switching. That means t equal to 0, you can always assume that the capacitor is like a short circuit. It's like a connector. But if it tells you in steady state meaning at t approaching infinity, you can assume the capacitor is like a broken wire. So there is no current flowing in that branch. The branch that has the capacitor, when t reaches infinity, there is no current flowing through it. Okay, we will do maybe a couple of examples of this. So this is very important. The nice thing is we have the mathematical equation of the charge, and we have the mathematical equation of the current. Okay, but sometimes it's not interested at what are the values here. It's interested at the values right here. Okay, or when t approaches infinity. So you can do a simplification. If you are doing it at t equal to 0, you can assume as if the capacitor is a short and just a connector and solve. And if you are going to t equal to infinity, you can assume the capacitor is like an open so there is no current will be flown and solve the problem. So these are tricks or simplification tricks in order to analyze a capacitor circuit at time t equal to 0, just when you switch, or at time equal to infinity in steady state. Okay, so this will become clear with the examples. Okay, so let's summarize. Charging a capacitor. When you charge a capacitor, this is how the charge behaves. It increases exponentially. The current is the derivative of the charge with respect of time, so you get an exponential decay. This is the only tricky part. The charge is increasing and the current is decreasing. It's kind of counterintuitive, because we know I is dq dt, but verify that mathematically. If you take the derivative of this equation, you will get this equation. So the charge is increasing and the current is decreasing. The voltage, the nice thing, the voltage is also increasing exponentially, because V is Q over C. Remember, Q is equal C delta V. So this is what we're plotting. We're plotting the potential across the capacitor. It's also increasing exponentially like the charge. The only tricky part is the current. The current starts at a constant, at a value, and then it decreases exponentially. All right? Now, remember, at t equal to 0, the charge is equal to 0, the current is equal to the EMF divided by R, and the potential across the capacitor is 0. The potential across the capacitor is 0. At very large time, at t very large, in steady state, the charge becomes maximum. It's C times epsilon. The current becomes 0, and the voltage of the capacitance becomes equal to the voltage of the EMF. Remember, we said when you charge a capacitor, the equilibrium will be reached when the voltage across the capacitor is the same as the voltage of your EMF in this one single loop circuit. Okay? So we already spoke about the time constant. The time constant is when t is equal to RC. When t is equal to RC, we said the current is going to be 0.63, the maximum value. The current is going to be 0.37, the maximum value, and the voltage will be 0.63, the maximum voltage. So these are, so this is at tau, which is equal to RC. Okay, you can see that the charge is 0.63 times the maximum charge. This is the maximum charge. At the, and the current decays exponentially. This is T is equal RC here. So if you go here, because it's exponential, minus RC divided by RC. So this is exponential minus 1. Exponential minus 1 is 0.368. So you get, this is the value. Okay, obviously you might also do the same thing for 2 tau, 3 tau, 4 tau, and so on. Okay, RC is the time constant, it's called tau, and the dimensions you can verify. R is volts per current, so that's volts per amperes, and the constant, the capacitor C is charge per unit voltage. So then you end up in this, the end, the voltage will cancel. You have Q divided by I is Q over T, so you end up with a unit of time. That's why RC, you multiply the resistance times the capacitance, you will find a unit of seconds, if the resistor is in ohms and the capacitor is in farads. Okay, so how about discharging capacitor? So let's assume now we have charged the capacitor and we reached a certain charge and potential across the capacitor. Now we want to use it, for example, a defibrillator, we want to use it to start the heart of somebody who had a heart attack. Okay, so now what we're going to do, we're going to switch to this position B in order to discharge the capacitor, and that's what we're doing here. Okay, and let's do the same thing. So now the circuit is simpler because we have only a capacitor and a resistor. So if I write my loop equations, it's very similar to the previous one. Notice I assume the current in this direction, which you will see is the wrong direction later on. Okay, because normally the current is going to be flowing out of the positive terminal of the capacitor, but it's okay. We can solve it and then correct it. We want to determine what is the charge in the capacitor as a function of time. So let's write the loop equation. Let's start at this point. Okay, let's start at this point. We're going through the capacitor, so the potential is Q over C, and we're going through the positive terminal of the capacitor, so the potential decreases. That's why I have a negative sign. Then I go through the resistor in the same direction as the current, so minus Ri is equal to, I went back to the same point, so this is equal to 0. Again, this is a differential equation. I can replace I by dq dt. Now I can rearrange the terms. dq over q is minus 1 over rc dt. I can do the same trick as I did earlier. So this is, if I take integral of dq over q is equal minus 1 over rc, the integral of dt. The integral of 1 over q is log of q. So, and to account for the initial condition, I put q initial here. So let's assume that the initial charge is qi. And when you solve, if you take the exponential of both sides, you will find that this is the final equation. The charge now is equal to the initial charge on the capacitor times exponential minus t over rc. It decays. So the charging is an exponential increase, the discharging is an exponential decay. So when you connect it to a battery, you charge it to a constant value. Then you disconnect the battery and you connect it to a circuit, it will discharge. And it's an exponential. If you want to determine the current, you can also take the derivative of the charge with respect of time. And notice now the current is minus q divided by rc exponential minus t over rc. Okay, so this is the current. Because of the negative sign, that means the current direction I assumed is wrong. Because I have a negative sign. So really, I can correct that. Okay, so this is our guess of the direction of the current is wrong, so I can cross that. Okay, and I can put the current in the opposite direction. So really the current is in this direction. All right, but I can do that at the end. Okay, so now I have the if I take my current in this direction, the equation for the current becomes I is equal to Q0 divided by RC exponential minus T over RC. Okay, and the voltage across the capacitor is V is equal to Q over C. Since I have the equation for the charge, I can replace it and I obtain. So the nice thing now, the current, voltage, and the charge, all of them are decaying exponentially. So let me go this and show you this. This is a charge. When you discharge the capacitor, it's Q equal Q initial charge, exponential minus T over RC. The current, you can get it by taking the derivative of the charge with respect of time, or the C dV dt. You get I, the current is the initial charge divided by RC, exponential minus T over RC. It's still an exponential decay. The voltage, same thing. The voltage, you can determine the voltage across the capacitor is Q over C, and so it is also an exponential. So these are three exponential decays which make our lives easier. Unlike in the previous example of charging capacitor. Remember, when we charge the capacitor, oops. When we charge the capacitor, we had the charge doing an exponential increase, the current was an exponential decay, and the voltage was an exponential increase. So charging and discharging are different. Okay. Don't know why it's capturing my voice. Okay. Now at t equal to 0, notice the charge is equal initial charge. The current is the initial charge divided by RC, and the voltage is the initial charge divided by C. At time t equal to 0, all of these parameters are 0. At t goes to infinity, the charge is 0, the current is 0, and the voltage across the capacitor. So, in other words, when you discharge the capacitor and you wait long enough time, at the end there is no charge across the capacitor, there is no voltage across the capacitor, and there is no current flowing out of the capacitor. Okay? Clear? We will do some problems tomorrow and solve some problems, and we're supposed to finish the next chapter, but okay, we're late. We will try to catch up. So, if you want to see your exam, you can come to my office, or you can come tomorrow morning. I will be in across this building in room 2011A. And please, the students who have less than 15, please come see me in my office as soon as possible. Okay? You can either come tomorrow morning here, or you can come to me, or you can call me in Microsoft Teams. You don't have to come in person. You can call me in Microsoft Teams. If you don't come, I will send you an email and ask you to come. So please, don't make me send emails to everybody. You have 15 or less in the exam, I want you to come see me. Yes?
For those equations, we have to derive them or just take notice?
No, you don't have to derive these equations. You should know them. Derivation, it's a differential equation. We don't expect you to solve the differential equation during the exam. But you have seen it's not a difficult one. نعم؟ نعم؟ ليش ما ذكرتنيش من الأول يعني؟
أنا هلا جيت متأخر
مش مشكلة. نسيت الأتندنس دي. خلاص. So everybody is present today. Next time you remind me at the beginning. شكرا.